Welcome to The Explainer. Today we're going to tackle a classic chemistry puzzle, one that honestly trips a lot of people up. What actually makes an acid dangerous? Is it because it's strong, or is it because it's concentrated?
Yeah, when you picture some scary bubbling acid, you probably use words like strong and concentrated, right? Maybe even at the same time. Well, here's the thing. In chemistry, those two words mean completely, totally different things. So let's break it down.
See, most of us in everyday life, we kind of use strong and concentrated interchangeably. But nope. Strength, that's all about the nature of the acid itself. Think of it like its personality. Concentration? That's way simpler. It's just about the amount of acid you've packed into a solution. Okay, so let's dive into this and really untangle the potency puzzle. We'll start with concentration, because honestly, it's the easier one to get your head around. So concentration, it's really just the amount of something, like an acid, that's dissolved in a specific amount of water. Think of it like making a drink. The more powder you dump into your water, the more concentrated it is. It's as simple as that. How much stuff is packed into the liquid? So you can have a concentrated solution where there's a whole lot of acid per unit of volume, or you can have a dilute solution where there's just a little bit. It's kind of like a packed subway car at rush hour versus an empty one late at night. One's concentrated with people, the other is dilute. Okay, now for strength. This is a totally different ballgame. Strength isn't about how much acid you have. It's about the acid's innate behavior. It's a measure of how much an acid molecule splits apart, or ionizes, when it hits the water. It's about its personality, really. And I love this analogy. It makes it so clear. Think of it like this. Strength is the punching power of one single boxer. Concentration is just how many boxers you've crammed into the ring. So you could have a ring packed with 100 really weak boxers, or you could have just one heavyweight champ all by themselves. See the difference? All right, let's get into the nitty-gritty, the science of what's actually happening when these acids hit the water. This is what chemists call ionization. So here's how it works. You add an acid to water. The acid molecules then split apart. They ionize. And when they do that, they release hydrogen ions, or H+. And those H+ ions are what make the solution acidic. That's the key right there. Now, a strong acid, like hydrochloric acid, or HCl, it completely ionizes in water. What does that mean? It means pretty much every single molecule of HCl you put in the water breaks apart. It's an all-or-nothing deal. Take a look at the reaction here. You see that arrow? It only points in one direction. That's super important. It means when the HCl molecule splits into H+ and Cl- ions, that's it. It's a one-way trip. The split is final. But a weak acid, like ethanoic acid, that's the stuff in vinegar. It only partially ionizes. It's way more hesitant. Only a small fraction of its molecules actually split apart. The rest just hang out, staying whole. And check out the arrow for this reaction. It goes both ways. That tells you this is a reversible process. The molecules are constantly splitting apart and getting back together. It's like a constant dance. The big takeaway? There are way, way fewer free-floating H+ ions at any given moment compared to a strong acid. And hey, this whole principle, it works exactly the same for alkalis, which are basically the opposites of acids. Strong alkalis, like sodium hydroxide, completely split up to release hydroxide ions, and weak alkalis, like ammonia, only do it a little bit. Same rules apply. Okay, so this is all great, but how do scientists actually tell the difference? I mean, you can't exactly see the molecules splitting apart, right? So how do you test it? Well, there are a couple of really clever methods. The trick is, you have to start with solutions that have the same concentration. Then, you can measure two things, the pH and the electrical conductivity. Let's look at conductivity. So, for electricity to flow through water, it needs charged particles, ions, to carry the current. A strong acid, which is chock full of ions because it completely splits apart, is like a superhighway for electricity. The weak acid, though, with only a few ions hanging around, that's more like a slow, bumpy country road, much lower conductivity. So it all comes down to this. More ions means a lower pH, which means more acidic, and it also means higher conductivity. So a strong acid will always have a lower pH and conduct electricity better than a weak acid of the same concentration.
Okay, we've got all the pieces of the puzzle now, so let's go back to that original mess and bust it once and for all.
You might see a statement like this on a test. All concentrated acids are strong acids. It's a classic trick question. So, is it true? No, absolutely not. It's a common misconception, but it's totally false. After what we've just gone through, you know that strength and concentration are two completely separate properties. So let's wrap this up. The key takeaways are: strength is all about the degree of ionization, the boxer's punch. Concentration is about the amount of the acid, the number of boxers in the ring. This means you can totally have a strong dilute acid, and you can definitely have a weak concentrated acid. The most dangerous acids, the ones you really have to watch out for, well, those are the ones that are both strong and concentrated.
So I'll leave you with a question to think about. Knowing all this, what do you think would be more hazardous in a lab spill? A whole bucket of highly concentrated but weak acid, or just a little cup of dilute but strong acid? The answer might surprise you now that you've figured out the potency puzzle.